Why so scandalous? Well, for starters, if we just reverse the letters that we use for our abbreviation, obviously it's going to spell a word that makes students snicker. But side, side, angle, angle, side, side, whatever way you look at it, this type of triangle causes a lot of problems when we get to the section of law of sines and we are solving triangles, finding all of the missing sides and missing angles. In problems like this, you'll always start with 3 pieces of information and you'll find the remaining 3 pieces of information. There's cases we'll use law of sines and cases where we will use the law of cosines. So let's just start off by addressing parts of an angle side side triangle on a diagram. Everyone can draw their triangle in their own way. I believe in consistently putting pieces together in the same way when you have a tricky situation so that you can ensure that your hand remembers it, your eyes remember it, your brain remembers it, because even though you will try to consciously just remember it, it doesn't work out that way. It takes a lot of things working together to guarantee that you can remember something tricky like this. I also always start with A and go in the order of ASS because I genuinely believe that you are more likely to store something at the front of your mind if you are giving yourself a reason to. If the spelling of the word ASS is a reason for you to remember, hey, this is the situation where tricky things happen and I actually have to watch out when I'm solving that I don't just approach it like any old solving a triangle problem, then so be it. If spelling ASS helps something stick in your brain a little bit better because it's not something you traditionally do in geometry, algebra, or pre-calculus, then go for it. Use that order to help yourself remember. I always start with the angle, and I always put my given angle in the bottom left corner. Then I need 2 sides. It's important that I don't do the sides on either side of the angle by mistake. If I want angle side side, I'm going to start at my angle. I'm going to go up to the right on side C to vertex B, and then from vertex B, I'm going to go down to vertex C. That's side A. Side B down here, even though it is the only side length we don't have right away, it's actually super important that we remember it has to stay fixed exactly where it is. It cannot move because it will compromise the measure of the angle. Remember, angle A is one of the 3 pieces of given information. There are a lot of truly moving parts in triangles that we are solving. However, if we are looking at the given pieces of information, those measures, lengths, values are not up for negotiation. They're given, they are what they are. We cannot bend. We are locked in. We signed the contract. That's it. We cannot move side B. We can figure out its length. That can be adjusted, but where it's placed in relation to vertex A cannot be adjusted whatsoever without messing up the angle, so you leave it alone. So I always keep side B as a horizontal line with a fixed position but an undetermined length. That was a very detailed explanation, but that's how I create the angle side side diagram for every single example, whether or not the numbers really make sense to that scale. So here's just a little color coordinating. If you're going to watch my videos, I promise you I will use this same method every single time, so it will be really helpful to you if you do what I do, so you could follow along with me, okay? The next thing I want to bring up is let's try to figure out when was it that you first learned about these abbreviations, side, 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 angle, 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 side. What unit was that? What were you learning? What were you doing? If you were able to think back, you might remember that you were learning how to prove 2 triangles congruent. And there's always a student who asks, or at least wonders, if there is an angle side side situation. Teachers usually squash this so that students aren't just left wondering about this the whole entire time, that they are actually supposed to be learning about something else. So, okay, fine. We're not allowed to use angle side side to prove triangles congruent. So why are we talking about it right now? Well, right now we're not trying to prove 2 triangles congruent. We're trying to solve triangles to find all of the missing sides and angles. This is trickier because the fact that we can't use angle side side to prove triangles congruent basically tells us that you can have more than one triangle with the same exact angle, side, side values. Okay, great. So, what does this mean for you? Why are we having such a long, heavy conversation about this scenario? Well, this means you need to recognize the situation where you may potentially have more than one triangle with the given measurements, and you need to know exactly what needs to be done in order for you to solve all possible triangles with the given angle side measurements. Problems don't solve themselves. If they did, they wouldn't be problems. You have to make it happen, and if you don't take the steps needed to solve, you will not get the right answers. All of the responsibility is really on you. We're going to see that this is even trickier than you might believe because not every angle side triangle gives us more than one answer. You may get one triangle out of it. You may also get two triangles out of it. And you actually may also find yourself in a situation where there are no possible triangles. You need to know what's going on. We're going to experiment with a bunch of different combinations of angle measure and side lengths so you can see how these all play out. Let's get to it. I've set up angle side triangle in a very early stage for us right over here. I've laid out a protractor where we're measuring angles. This protractor is set, here's 0, 10, 20, 30 degrees. So that means the angle right here is set to 30 degrees. This side down here is like the side I had as side B in the drawing before, like this, okay? This right here said B. I want you to think of side B, this bottom right here, as sort of like a ledge. A ledge where this stuff is propped up and resting on it, and it goes on for quite some time in both directions. We just have to figure out how big B has to be based on the other information. So we just treat it as a horizontal. You could also think of that as the invisible horizontal line we saw when we were learning about angles of elevation and angles of depression. Why do we need that line in there? Well, if you don't have that line there, you can't accurately set your angle. Does that make sense? You need that line here so you can determine your angle. This side length is predetermined, and then the other side that I'll put over here will also have a length predetermined by the information in the problem. So let's get looking at a bunch of different scenarios so that we can understand what happens and why. This piece I have here represents a line segment with length 1, 2, 3, 4, 5, 6 units long. This is side C in my picture. Side B, I don't know the measure of. Angle A, I allowed it to be 30 degrees. I'm going to play around with a few different values for this green side A. We're going to see what happens in each case. I'm going to write down my 3 vertices. I'm also going to write down my 3 sides. We have 30 degrees. We have that side C is 6 units, and we're going to play around with a few different values of X. Here, I have a segment that's going to be 3 units long based on this scale that I used to make the other one. If side C is 3 units long and I try to attach it, let's see what happens. Now remember, I can't attach it any way I want. That's why having something tangible that you can actually touch is really going to be quite helpful. I can't just put it anywhere I want and then pull side B in and call it a day. If I close these together more, well, that's no longer 30 degrees. That's why these can't move. These are taped down, okay? They're not going anywhere. This is going on. We're going to attach it. We're going to see where it touches this because this side B, must be here in order for this to be 30. And then we kind of discuss from there. So if I put this in, I need it to touch side B, and it looks like it touches it right about there. Could I make 2 triangles from this situation? Look at what I'm outlining here, all right? I got this side, like this, and this. I want you to keep this visual in mind. Here I have another line segment. This line segment represents 1, 2, 3, 4, 5, 6, 7 units. Example 2, we're going to have a case where the side A piece, which I have a model of or the prototype of right over here, side A will have a length of 1, 2, 3, 4, 5, 6, 7 units. Now, I can't try to connect this straight down because it extends beyond side B. You need to sweep this out and make the angle B larger, and this has to just touch side B. So give or take, there we go. This will be example 2. So the inside, this is angle A, angle B, now it's more of an obtuse angle up here, angle C, side A, 7, side C, still 6. Side B is definitely a different measurement than it was in the previous scenario. Is there another way to put this angle of 30 degrees, this side length of 6 right next to it, and this side length of 7 together in another way? Example 3, we're going to allow side length A to equal 2. So here I have a little segment, and this piece has the length of 2 units. Now if I try to attach this up here, I have 30 degrees, 6 units, and 2 units. I need to attach this down to side B, which is necessary to create that 30-degree angle. What seems to be the issue? The issue is it doesn't reach. This means that there's no triangle. How do you know that there's no triangle while you're trying to solve? Well, this is something we'll explore in example 3. And in example 4, the last side length, we have a segment for A that has a length of 4 units. If I connect this one, it's like it needs to be just about there. Is there another way I could put this triangle together? Is there more than one triangle that I could potentially make? What I'm going to do is I want for this to stay there, but I don't want to push pin it with the wrong spot, So it's going to end up getting pushed in just a smidge past itself. You see how I'm able to swing this open? Well, this is one triangle. I'm able to swing it right over here and create a second triangle at the same dimensions. I still have 30 degrees. I still have a 6-unit side, and I still have this 4-unit side. I have not compromised anything. This is part of what makes an angle side-side triangle so scandalous. So we could potentially make one triangle. Perhaps we can't make any triangles. Or maybe we can make 2 triangles. Very tricky, very sneaky. And the issue is, unlike a factoring problem where the 2 answers just sort of pop up and present themselves to you automatically, you have to do specific steps to solve for that second triangle. The calculator and your calculations and the work that you're going to do is only going to give you one triangle, and it's up to you to recognize that this is the situation that you're in and that you need to go ahead and find that other angle. I'm going to give you a few pointers. We're going to use the word ASS to help us remember. And let's get into these examples now. Example 1. Solve the given side-side angle or angle side-side triangle. A is 30 degrees, side A is 3, and side C is 6. Now, I've set up a picture here, and I'm going to reuse this picture for all of them. The issue is, most of the time when you're solving a problem like this, you'll have pen, paper, calculator. You're probably not going to have a ruler or a protractor to actually make things to scale. I'm showing you these things to scale today because I want you to understand why things work out a certain way. However, realistically, if you were solving this question, I would say, first recognize that you have an angle side-side triangle. Then, when you go about solving, you're really just drawing an arbitrary triangle. I would say more often than not, I end up drawing a fairly equilateral looking triangle because it really doesn't matter. Here I have A, which was given to us as 30 degrees. Angle B up here, angle C, side A given, which was 3, and side C is given 6, and side B, we don't know. So you're probably going to end up drawing something like that, an angle, side situation. Certain criteria are going to cause more interesting things to happen. We're going to discover that as we go. When you're solving triangles, in the first objective lesson, when we solved angle, angle, side, and angle, side, angle, triangles, you were given 2 out of 3 angles. So my advice to you is to always find that third angle. However, this time we have only 1 angle and we have 2 sides. You're not going to be able to find the third side magically. If you use Pythagorean theorem, that means that you're assuming one of the missing angles is 90 degrees, which is not necessarily the case. So we have to skip that first step. The next step is to determine which perfect pair we have. We have both A's. That means we're going to use A and A. Then, should we try to solve for angle B, side B, or angle C? We're going to solve for angle C because we have to use 3 pieces of information in your equation in order to solve for the fourth. You can't have 2 unknowns. We're solving for an angle. The other advice I gave was that when you're solving for an angle, you should use sine of the angle in the numerator in order to make the problem as easy as possible for yourself. I'm going to use sine A over A equals sine C over C. Now I'm going to fill in everything that I know. I need to solve for angle C. I need to get C alone. So the first thing you should do is multiply both sides by 6. 6 just happens to reduce with 3. That won't always happen, but this time it does. 6 divided by 3 is 2, so we have 2 sine 30 equals sine C. If you know the unit circle, which you'll learn in either in algebra 2 or in calculus, you could more or less solve this triangle, no problem, no calculator. If you're a very good observer and you paid attention to the information you were given from the very start, you could also solve this triangle without any further information. However, we're going to just roll along with the law of sines. From here, you would normally punch this in a calculator and get a decimal value, or in this case, you're going to get a whole number, but either way, you get a numerical value. After you get this numerical value, you still need to solve for C. 2 sine of 30 will give you 1. Whether it equals 1 or it equals some crazy decimal, we need to get angle C solved for. How do we solve for angle C? Every time you isolate a variable, what you're doing is you're using the inverse operations to peel away all the layers, sort of like Shrek.
Ogres are like onions.
And his whole spiel to Donkey about the onion.
Layers! Onions have layers. Ogres have layers.
I need to take sine inverse of both sides. The sine inverse of sine C, adios, and now we just have capital C. And sine inverse of 1, you'll type that into your calculator. On this calculator, if I wanted to use sine inverse, I just double click. Sine inverse of 1, closing that parenthesis, 90 degrees. And if you notice, it says deg, which means my calculator is in degrees. So that's 90 degrees. Angle C is 90 degrees. If angle C is 90 degrees, what should we do next? Anytime you have 2 out of 3 angles, find that third angle. We are working with a 30, 60, 90 triangle, and this is why some of you may have been able to solve this triangle without the law of sines. If you recognize that you have 3 and 6 and 30, that 3 and 6 would represent x and 2x, this side would be x root 3, which is 3 rad 3. That's super precise and super awesome. What if you didn't recognize that? How would you proceed with law of sines to find the length of side B? We're going to set up law of sines again, but this time we're solving for side B, so we need lowercase b in the numerator. B over sine of B, which is sine of 60, equals, and then I always go back to my original information. In this case, we haven't really rounded anything, but I'll still go back to 3 for A over sine 30 for sine of A. How do we get lowercase b alone? In order to get this lowercase b alone, I need to multiply both sides by the sine of 60. B will equal 3 sine 60 over sine 30. I know 30 and 60 look pretty nice above each other, and you might be tempted to reduce. However, you can't reduce those. When you have the sine of 60 and the sine of 30, you can't simplify. If I wanted to type in the calculator and figure out the answer for the length of side B, I would go ahead and type in 3 Sine 60 divided by sine 30. On this calculator, the way the settings are right now, if I just go ahead and hit enter, it's going to give me an exact solution. 3 root 3. That's exact. I didn't have to round. I have a radical in my answer, but it is what it is. What if you needed the decimal and your calculator is giving you a radical? Most calculators, what you'll do is you're going to hit second and then enter. However, on this calculator, I do have a little approximately equals sign. Now let's see, right over here. That's telling you it's an approximation. So if you see an approximately equal sign, or if you see the word approximately, you'll use that. So I'm going to hit that button instead, and it gave me 5.196152423, yada, 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 that goes on. So B is approximately 5.2 units, and I'll just include both of those in my answer. In this case, we only had one triangle. The first angle you get really more or less dictates how many triangles you're going to have. Time for example 2. Example 2, we said we'd use a 30-degree angle. We'd use side A as 7 and side C as 6. When you're faced with this question, you're not going to have measuring devices handy. You're just going to sketch something out and just go for it. If you had 2 angles, you'd go ahead and find that third angle. We don't have 3 angles, so we're going to look at what pair we have. We have both A's, angle A and side A, and that means we are going to find the angle that corresponds to the side we have. We are going to find angle C yet again, basically every single time in this scenario. So we're going to have sine of angle C over 6 equals sine of 30 degrees, or angle A over 7. From here, we want to get sine of C alone before we get C alone. We're going to multiply both sides by 6. In the previous example, multiplied by 6, it happened to reduce quite nicely, but like I said, that won't always happen. Sine of C will equal 6 sine 30 degrees over 7. This will go in the calculator. We will get a decimal on our screen. I'm going to type in my calculator 6 sine 30 divided by 7. Here I got 3 7s as my answer because the calculator knows that's the precise answer. I want the decimal solution for right now, 0.429-ish. Now, I have here that this fraction is approximately equal to that decimal, or it actually equals this fraction right over here. To solve for C, we take the sine inverse of both sides. I could take the sine inverse of this, as long as I use parentheses, of this, since it's already on my screen, or of this, as long as I use parentheses. If I take the sine inverse of the decimal that's already there, I get sine inverse on my screen. I'm going to use the up arrow to highlight the number I want. That basically copies and pastes it. When I hit enter, close my parentheses, and I hit equals, and I get 25.4 degrees. Now that you know angle C is approximately 25.4 degrees, I'm going to use my 2 angles to find my third angle, angle B. And once I have angle B, I'm going to find side 30 plus 25.4 gives us 55.4. And 180 minus 55.4 will leave us with 124.6 degrees. Last thing I need to do is find side B. B over sine of 124.6 equals, here's where I go back to my original dimensions, so 7 over sine of 30. I don't need to use trig inverse for this question, so it's a little bit easier. I'm going to multiply both sides by the sine of 124.6. That means B equals 7 sine 124.6 over the sine of 30. Now in the calculator for this question, what I typed in was 7 sine of 124.623066. So I actually ended up doing in the calculator 180 minus 30 minus this whole big number I wanted to be more precise. I got the angle rounded out further. I did 7 sine of that angle over sine 30. Hit enter. We get about 11.5. Here I have side length 7 set up in place with my 30-degree angle, my length of 6 on this side. And we saw one example, which will be example 4, where we were able to swing this over and create a second triangle. But do you see what happens with the length of 7 if I try to swing it in? Am I able to still make that second triangle? Why or why not? What circumstances are impacting my ability to make that second triangle? Well, the fact of the matter is, while this side is long enough to make a triangle, it's too long for me to swing in. Where is the cutoff? What's the longest this side could be in order for me to be able to swing this in, right? Like, what should it be? We also saw in the last example that this length made a right triangle, which also can't swing in. This is too big. This is too small. Anything bigger than 3 units, we're good to go. Not because 3 is half of 6, but because 3 makes it a right angle. Whatever measure will cause this to be a right triangle, that's the smallest you can have to create one triangle. Anything shorter won't reach at all. Anything between 3 and some number will be able to swing into 2 triangles. Where is that cutoff? I wonder what it could be. What if this is also going to have a measure of 6 units, the same length as side C? So I'm going to attach it over here. Now can you see a second triangle in this situation? That's angle A, B, and C, and then side length A and C are the same, and then side length B will be down over there. If I were to swing that all the way back around, I could have an isosceles triangle. This can't swing in, but anything shorter than this can. So anything less than 6, but greater than making a 90-degree angle, can create this ambiguous case where we can create 2 triangles. Here we have example 3, which was the length of 2, and if you recall, when we had that segment of length 2, it was not able to reach, and we were not able to even create a triangle. So what would happen if we were solving with law of sines that would tell us, hey, knock it off, this isn't even going to make a triangle, just cut it out, right? So we have the same setup. We have our pair of A and A, and we're going to look for angle C first, just like the previous examples. So I'm going to set this up with the sine of C over 6 is equal to the sine of 30 over 2. Now really, the calculator is going to do its magic. After we multiply both sides by 6, you'll figure out the decimal value by using a calculator. You take sine inverse of both sides. Sine inverse will come next, right? Let's look at what it is we're going to be taking the sine inverse of, shall we? In the calculator, you would type in 6 sine of 30 divided by 2, which is the same as 3 times the sine of 30, 3 over 2, or you use a different calculator and you'll get 1.5 right there. 1.5 is a precise number because it's a terminating decimal, but you'll often get these irrational numbers. You need to take the sine inverse of this value, so sine inverse of that 1.5. When you try to do this in your calculator and you go to hit enter, that's when you know you can't make a triangle. Your calculator is going to tell you error, domain error, something along those lines. Basically, it's a way of saying you can't make an angle. Sorry, not doable. If you are in a higher level math class, if you're in a higher level math class, you know that the sine inverse can only be taken of values from -1 to 1 inclusive, or that you cannot take the sine inverse of anything greater than 1 and anything less than -1, because sine is opposite over hypotenuse. You can't have an opposite over hypotenuse be bigger than 1. So that's another giveaway. But if you're only in geometry, there might be nothing to you. So you just need to know that when the calculator yells at you and tells you there, that means you can't make a triangle. And that's the end of example 3 because there's nothing you can do from there. So you might just write no triangle possible. Example 4. Solve the given side-side angle or angle-side-side triangle. Again, for the 4th time, we have a 30-degree angle and side C is 6 units long, but this time we're using side A is equal to 4 units. We have a set of A values. We have 30 degrees and 4 units, so when we set up our law of sines, we'll be using the A values for one side of the proportion, and we'll be using the C values for the other side of the proportion since we have both A values and we have one of the 2 C values. Since we're solving for an angle, we'll put the sine of C and sine of A up in the numerators. We need to get sine of C alone. We'll multiply both sides by 6. We have 6 sine 30 over 4 equals sine of C. In order to get C isolated, we have to take the sine inverse of both sides. You could calculate 6 sine 30 degrees divided by 4 in your calculator first. If you do that, you will get 3/4 or 0.75. Now, if we take the sine inverse of both sides, the sine inverse of sine C will just leave us with C. The sine inverse of 0.75 is not really the type of thing we do in our head, so we're going to grab the calculator to do that as well. When all is said and done, we're going to find that the sine inverse of 0.75 equals 48.6 degrees. If angle C is 48.6 degrees, and angle A is 30 degrees, that means that angle B has to equal 101.4 degrees. Last, we'll set up law of sines one more time to find the approximate value of side B. Since we're solving for a side value, we will put B in the numerator and sine B in the denominator. Once again, I'm going to default to using the A values for the other half of this proportion since those values were given and they are not rounded. After multiplying by sine of 101.4 on both sides to isolate the B value, we use the calculator once again to find that B is equal to approximately 7.5 units. Now we have fully solved one possible scenario of a triangle with the dimensions 30 degrees for angle A, 6 units for side C, and 4 units for side A. However, this is only one possible scenario. As we've been discussing and as we saw earlier, this side length of 4 units possesses exactly the right characteristics to allow it to sweep in and put together another triangle that still maintains those traits. Now I'm swinging it in, showing where it would potentially land, and I'm going to highlight both of these side lengths in green because it's important that we realize that these two possible placements create an isosceles triangle. Isosceles triangles possess certain characteristics that we are quite aware of, most importantly being that the two base angles are congruent. One base angle we are aware of is 48.6. That means the other base angle is obviously also 48.6 degrees. The angle we're looking for is actually going to be adjacent to the left base angle and inside of this little sliver of a triangle. If it is adjacent to it, it is the linear pair. If it's a linear pair, that means it is a supplement, or we can calculate its value by 180 minus 48.6 degrees. Now I'm going to set up capital A, B, and lowercase a, B, C So I can start filling in the values for my second triangle. A, and lowercase c are obviously the same because those are given. Angle C, as I just explained, will be equal to 180 degrees minus 48.6 degrees, which is 131.4 degrees. Once you have two angles, you can find the third angle, and that third angle is 18.6 degrees. To find that last side, that's what we've been doing since the beginning of Objective 1, and finding missing sides using law of sines should be your expertise at this point. B over sine 101.4 equals 4 over sine 30. Under these conditions, isolating the b value, we find that b is approximately equal to 2.6 units. In example 1 and 2, we solved angle side-side triangles, which only had one result. Example 3, we weren't able to make a triangle, and here in example 4, there were two possible triangles. All I'm going to do to finish this problem is I'm going to label my first set of information as triangle 1 and my second set of information as triangle 2. Next, I'm going to share with you a list of important things to look out for, criteria. Step 1, is the triangle an angle side-side or side-side angle triangle? Okay, if you can say yes. Is the angle side-side triangle biggest in the middle? Pun kind of intended. So I wrote it as a lowercase a, capital S, and lowercase s. That stands for, in my own little code, acute angle, a side, and then a side shorter than the previous side. So if you really think about the situation where we used a side length of 6 for both sides, which created really an isosceles triangle, and it created a situation where we could swing it in an attempt to make a second triangle, but it would end up just lining up and matching up with the existing side and not really able to create a second triangle. That length creates a cutoff, a boundary. Next, is the first angle you solve for solvable? So what do I mean by that? Well, if you look at the information we saw in example 3, it would have met the criteria. Number 1, is the triangle angle side-side or side-side angle? Yeah, it is. Number 2, is it biggest in the middle, angle side-side acute angle, 30 degrees, check. Side length, okay, sure, 6, check. Shorter side, you got it, 2, check. However, was the first angle we solved for solvable? We solved for angle C, and we got domain error. It was not solvable. If it's not solvable, that just means you have no triangle. If it is solvable, that means you have two triangles. So what can happen? Your side length could prove to be too short and you have no triangle, like it was when we had a side length of 2. Or your side length could be just enough to reach and form a right angle, like we saw in example 1, with the length of 3 in this particular case. Or it could be a little bit longer and it can make a triangle. But if it makes a triangle such that the side length we are using for the side opposite the given angle is less than the length of the side adjacent to the given angle, in those cases we will make two triangles where the second angle for angle C is found by 180 minus the answer we got the first time, or the side length across the given angle is greater than the side length adjacent to the given angle, and in that case you only have one triangle because you cannot swing it in to make another triangle like we saw in example 2. I hope this helps you. I hope you're able to go back and rewatch important parts, and hopefully I can put together something shorter as a quick refresher, but I think it's important that everyone has solid examples to follow and reference and a very detailed explanation. Good luck.